Hey, today we're going to start with the idea of the line tangent to a circle at a given point on the circle and generalize that to a concept of the line tangent to curves that aren't circles at points on those curves. So let's get to it. Okay, start with a circle, pick a point on the circle, and there's only one line through that point tangent to the circle at that point. And there's various ways to think about it, but one common definition is it's the only line that touches the circle in exactly one place, which is that particular point. Any other line either misses the circle entirely or goes through the circle in 2 points. And if we zoom in on what's happening in the region where the tangent line touches the circle, then you get something that looks more or less like this. And if you zoom in even further, you start to get something that looks more and more like the circle itself, to the point where if you continued this process indefinitely, the tangent line and the circle would become virtually indistinguishable from each other. And so, in a sense, the tangent to a circle at a point is the line that gives the slope of that circle if you were to continue zooming in to so far so that the circle looked flat. In other words, imagine the Earth, for example, to go into 3 dimensions, is a perfect sphere. No mountains, no buildings, no cars, no people, no rocks, trees, etc., but just a perfect giant sphere. And then drop yourself on it somewhere, carefully, and look around at the area right around you for a few feet. You would not be able to tell that it wasn't perfectly flat. Same thing in 2 dimensions with a circle. Zoom in far enough and you can't really tell that the circle isn't perfectly flat. And the tangent line at that point just gives you the slope of the line that the circle would be if it were really perfectly flat, not just at that point, but on and on forever. So that's the basic idea of the tangent to a circle at a point. Now we want to do the same thing, come up with the idea of a tangent line to an arbitrary function, in this case this function f, at some point a, or more precisely at some point a f of a, where a is the x value and f of a is the y value. But we can't use the same idea that we could for circles of only intersecting the curve once. That doesn't work. Because, for example, here's a line that only intersects the curve precisely once at that point a f of a, but is certainly not what we intend for a tangent to the curve at that point. On the other hand, if we use the idea of zeroing in, narrowing in closer and closer to where the curve looks flat, this curve here is more of what we actually have in mind for the tangent to the curve at that point, and yet it intersects the curve in more than one place. And so that definition from circles won't work. And so we need a new one. We start with the idea of secant lines. We pick some arbitrary point x, and we look at the point x, f of x, and we draw the secant line from a f of a to x, f of x, secant line just being a fancy name for a line that connects 2 points on a curve. It's easy to compute the slope of this secant line. It is, as always, the slope is the change in y over the change in x. And in this particular case, based on the x and y values, that's f of x minus f of a, the change in y, all over x minus a, the change in x. And you can think of this as an approximation for the tangent line to this curve at x equals a, but it's a particularly lousy approximation. And if we want a better approximation, one thing we could do is move x closer to a. And having moved x closer to a, we get this new secant line from a to x, or from a f of a to x f of x, and it's different from the other one, and it's maybe a better approximation of what a tangent line would actually look like. And we can keep doing that. I just did it again. I moved x even closer and got a new secant line. And the idea being, as we move x closer and closer and closer to a, we get these secant lines between tinier and tinier distances that become better and better approximations of a line that actually does give you the slope of the curve at the point A, as if the curve had been flattened out entirely at that point A. And so we're looking at essentially a limiting process. And this is where our definition of the tangent line to a curve comes from. It comes from taking the limiting process of these secant lines. And that gives us our definition. We define the tangent line to a curve y equals f of x at some point A, f of a, as the line passing through that point whose slope is the limit as x approaches a of f of x minus f of a all over x minus a. In other words, whose slope is the limit of the slopes of the secant lines as x gets closer and closer to a. And in our picture, we only had x approaching a from the right, but of course we also need to consider x approaching a from the left to have a two-sided limit there. Okay, before we proceed, it turns out there's a second way to do this that at first looks a little bit more complicated, but in the end turns out to be easier to work with. And so let's do the exact same thing, but slightly differently. And instead of picking a point x a little bit away from A, we pick a relatively small distance that we call h, so that the point A plus h is a small distance away from A. And we can again consider the secant line between these 2 points on the curve. And the slope of that secant line is, once again, the change in y over the change in x, which in this case is f of a plus h minus f of a, all over the change in x, which is a plus h minus a. And since a plus h minus a is just h, we can simplify the denominator a little bit and get this expression here. And then we do the same thing. What if you made h smaller? Well, in that case, you'd get a secant line through your new point a plus h that was a better approximation of the tangent line at the point x equals a. And you could keep on doing that and make h smaller and smaller and smaller and smaller, which is once again a limiting process, except that in this case, instead of as the limit being as x is approaching a, it's the limit as h is approaching 0. And that gives us a new alternative definition for the tangent to a curve at a point. In other words, the tangent to the curve y equals f of x at the point a, f of a is the line passing through that point with slope either the one that we said a moment ago or the limit as h approaches 0 of f of a plus h minus f of a all over h. And for now, we will use either and both of these formulas for the slope of a tangent line at a point. Eventually, it will become important for us to pick one of them, and we will end up picking the second one in the long run. But for now, we're going to use either and both of them. And this expression for the slope of a tangent line to a curve at a point is so important that we give it its own name and its own notation. We call it the derivative of the function f at the point A. And the notation is f prime of a, that little tick mark, we say prime. So f prime of a is either the limit as x approaches a of f of x minus f of a all over x minus a, or it's the limit as h approaches 0 of f of a plus h minus f of a all over h. Both of these things give you the slope of a tangent line to the curve y equals f of x at the point a, f of a. And I should have added when I gave you the definition that this is the derivative of the function at the point, provided this limit exists. The derivative of a function at a point is defined in terms of some limit. Limits may or may not exist, so if the limit doesn't exist, then the derivative of the function at the point doesn't exist. So just to be careful and technically correct. Okay, I want to do one quick example of how to use what we just figured out to actually compute the equation of the tangent line to some curve at some point, at which point you will know all you need to know to do the homework on this stuff, but there are some algebraic tricks that you will not have seen, and so there'll be a second video, no new conceptual material, but just going through a couple of examples so that you get a little bit of familiarity with some of the algebraic tricks in case they trip you up on your homework. So let's do one example and then we'll take a break. We'll see if we can't find the equation of the line tangent to the curve f of x equals x squared at the point where x equals 3. And here's a rough sketch of y equals x squared, the parabola, and we're looking for a line tangent to that curve at the point where x equals 3, and where x equals 3, y equals 9, so it's passing through the point 3, 9. So just to give us a rough idea, the line that we're looking for, something like this. So if we come up with an answer where the slope of the line is negative or something like that, no good. It's not going to, we can see that this has a positive slope. If we see that the y-intercept is 75, we'll know we have it wrong. So we'd like to get some idea that the answer that we come up with is actually correct. Okay, we're trying to come up with the equation of a line. We do know a point that it passes through, 3, 9, so all that's really left is to find the slope of that line, and we have 2 ways to find the slope of that line, so let's do it both ways. The first way, f prime of 3, the derivative of this function at the point 3, is the limit as x approaches 3 of f of x minus f of 3 all over x minus 3. In other words, all I've done is taken our first definition of the derivative of a function at a point, or our first definition of the slope of a tangent line at a point, and replace the a with 3, because in this particular case, the a that we care about, the point that we're trying to find the tangent at, is 3. And now it's just a matter of evaluating this expression and then computing the limit. In this case, f of x is x squared, so we can replace the f of x by x squared, and f of 3 is 9. And so we get the limit as x approaches 3 of x squared minus 9 over x minus 3. This is an easy and familiar kind of limit to do. We do it by factoring the numerator, in which case we see that a factor of x minus 3 cancels, and we're just left with the limit as x approaches 3 of x plus 3. And that's a polynomial, so it's a continuous function. We can compute that limit just by plugging in x equals 3, and we get that that limit is 6. So the slope of the tangent line is 6. And before we actually find the equation of the tangent line, let's find the slope of the tangent line through our other definition of the derivative at a point. And the other definition was that the derivative at 3 is the limit as h approaches 0 of f of 3 plus h minus f of 3 all over h. And again, all I've done is replace the a in our definition with 3, because 3 is the point that we are trying to compute the tangent line at, or find the derivative at. And all that's left is to evaluate this expression algebraically and then take the limit. And since f of x is x squared, f of 3 plus h is 3 plus h squared, and f of 3 is 9. Now we just expand the 3 plus h squared and simplify the results to get the limit as h approaches 0 of 6h plus h squared all over h, after recognizing that 9 minus 9 is 0. We're still not ready to take the limit because this is a rational function not defined at h equals 0, but we can do sort of the same thing we did the last time. We can factor the numerator. In particular, there's a factor of h in all of the terms of the numerator, so we can pull that out. And the h's cancel, and we're left with the limit as h approaches 0 of 6 plus h. 6 plus h is a polynomial in the variable h. In other words, it's perfectly continuous. We find this limit by plugging in h equals 0, and we get 6 just like we did the other time, which is a good feeling. These definitions are supposed to be equivalent, which they are, and so if you do it either way, regardless of which way you do it, you should get the same answer like we did. So we know that the slope of the line tangent to the curve is 6. And if we look at that orange tangent line that we drew, 6 looks reasonable. It's certainly a positive slope, and it's certainly bigger than 1, reasonably steep. Aside from the sloppiness of the drawing, 6, perfectly reasonable answer, and in fact the right answer. We're not done yet. All we found was the slope of the tangent line. The question asks for the equation of the tangent line. And we'll be doing this kind of thing a lot. The equation of any line is y equals mx plus b, where m is the slope. We just found the slope of the tangent line. It's 6. So we know that y equals 6x plus b. To find the equation of the tangent line, we have to plug in values for x and y and solve for b. In particular, we know that this tangent line passes through the point 3, 9. That's x equals 3, y equals 9, and so we can plug those in for x and y, and that will let us find b. And after doing a tiny bit of algebra, we find that b is equal to -9, and we are ready to give the answer. Y equals 6x minus 9 is the equation of the line tangent to the curve y equals x squared at the point x equals 3. Okay, as I alluded to earlier, you are now in excellent conceptual shape to do your homework on this stuff. There's no new concepts to show you. All that's left is algebra. So, I showed the example that we just did with the easiest possible algebra. Some of the homework problems, the algebra will be not hard, but certainly slightly trickier. And so if you're very confident in your algebra skills, just go straight to the homework. But if you'd like to brush up and see a few more examples, then there's a second video that shows some examples of computing slopes and or equations of tangent lines to curves where the algebra comes out a little bit trickier. All right, have some fun. See you soon.